Okay, so I think we'll start with rewriting this function because it caused some doubts, and maybe we should do it step by step so everyone will know what's going on there. What do we want? We want the gradient of our loss function with respect to our weights. So this is called here weight gradient. So we will roll back a little and just get rid of this. Okay, so if you want, so how does this work? The whole neural network is just the composition of this linear operator, or just matrix vector multiplication of weights and our input, and this is composed with our activation function, which is composed with our loss. So if we want to get derivative of this, then we may use chain rule. So maybe like this. So this will be derivative of our loss, but as input it will take our result from rest of the function composition according to the chain rule. So we have so this is just output of our neural network, so we may just substitute with, but maybe later, and this should be multiplied with derivative of the rest, so this thing. So this is just output. So okay. And this we apply chain rule again, so we have activation with respect to the output, derivative of activation with respect to the output of the linear transformation, composed with derivative of
composed and multiplied.
Multiplied. Thanks. So we need all these things. So, okay, at the beginning we need our input, not this input, but the input with const 1, because this is the proper input of our neural network. So let's call it. How did I call that yesterday? Vector cons, okay. Okay, so to have these nodes, okay. we will need derivative of our activation, but that's given by the div. So we will need this thing, this multiplication. So this will be pre-active. So let's call it so verbose, but I hope everyone gets what it is. And proper output, which is just this, but with mapped on it the activation function. So now the derivatives. This will be, let's start with this one. So this is the diff loss of output, which is our loss gradient function. So which is at the expected value with respect to the output. We want this one, which is quite trivial, so we take our derivative, so again vector map, but this time diff activation. And this is just the same multiplied with, because derivative of this multiplication is just our input, but to get the proper derivative we will have to get outer product of this, so we will have this was this, which has, oh okay, it was just outer product of this with input. Okay, let's see what's wrong here. Okay, so this is something which is not defined yet, but I think we should define it because it will come handy later. So we don't have num instance for vector, but this is something that we might need. So theoretically we could derive it with generalized new type deriving, but it wouldn't be proper definition because the default from integer for vector is vector of length 1. So this would disrupt our type safety. So I think this for all is not needed, but
Is this for subtraction?
I'm sorry?
Is this for subtraction? Is this for subtraction?
Is this for
No, this is just for because we will be using our loss function as function from two vectors to third vector, and we would like to use automatic differentiation there. And automatic differentiation is for functions which are polymorphic for numeral types. This is quite straightforward, so okay, maybe just do it by hand. So this is the main problem, so we can just use creating singleton list and from integer, so we have float. This, I think, is everything for num.
I just complaining about num not.
No, it's complaining because, okay, no explicit implementation for multiplication and signal.
There's always more.
Yeah. And it's just copy and paste. I had somewhere template for template Haskell to just get some wrappers and derive it from me, but whatever. So explaining this template Haskell would be longer than hold this talk. This is all, but there's some problem because there's minus instead of equality. Okay, it does not complain. Well, now we'll do the whole numerical tower. So it had division, so no, it's still not safe, so let's do it like this. It had from, it was fractional or rational?
Well, skip it and see what it will complain about.
I think it is.
Divide is fractional.
Okay, it's fractional because division is for fractionals. Okay. But it has method from rational, so this is why I was I wasn't sure. And here the same hack from here. So. But I think this will allow us to just derive the floating. Well, let's see if it compiles. I can see from my screen, so Okay, what do we have here which does not require this extension? I think nothing, so let's just see the
You should just load the file.
sorry?
Can you just reload the file?
It seems to be working, I think. So let's see. Okay, it's working. So this saved us some boilerplate. Okay, so is there anything problematic here? Because I think not. So this seems to be right. So we will see on some examples. So let's create some random network. So let's just see if, oh, okay, there's one problem for sure, because as I had a problem with yesterday with matrix dimensions, because I needed to flip them, the height with width, and I need to do the same with the outer product. So I wasn't sure yesterday, but I checked it today in the morning, and it needs to be swapped. It was a random layer, I think. Okay. Okay, so it just needs 2 nuts. We can use such a function, I think, just for testing purposes. Okay, but I want some vectors, so okay, we had our contact signal, so let's see if it will not hang, because lazy evaluation just still stops us from knowing if there's some problem or not. So let's just nothing better than some typos. Oh. So is it really like this? Okay, so I think I reloaded it and it's still the same. Okay, so it's working with the outer products flipped, so it's okay. So everyone has it. So some problem, something not readable. Should I increase the font size?
Can you upload the project so far in the Discord?
Okay, so I don't have Discord set up, so I forgot about this yesterday, and
It's we can do it now if you want.
Just this file only.
Or maybe as a Git on GitHub.
yeah, or maybe XIO. Will it be fine?
What is that?
On XIO to paste it, the quick link.
Yeah.
I posted the link on the channel. So when I try random network,
Oh, so there's problem with network or something?
so GHC says panic, the impossible happened.
Oh, sorry?
GHC says the impossible happened and it says panic.
Okay. Could you show me? Because
Also, I had to. This LTS was 11 point something, I guess.
yes.
I changed this because I have like 9.0 versions installed.
Okay.
If I try with this, like I get some other thing, like something like this. With 11.39, if I try Stacks GHC, I get this.
Okay, so it has problem with bytes. Oh, but it's problem with stack, I think. That it cannot parse. I had similar problems with stack.
So when I change it to 9.0 and then try, then this thing gives me this.
Okay, but okay. So this is GHC 802. So I do it on 822 and it seems to be working, so maybe it needs something more on the older version.
822.
Yes.
Okay. How can I update?
Yes, you're using stack, yes?
Yeah, because there was a stack file, right?
Yes. But so maybe stack upgrade or stack update, and then with the newer LTS? Because I think the Cabal file can be used without the stack, because the Cabal is generated by stack, but then you may just use it without stack.
I'll try.
So the typical Haskell ecosystem problems. Okay, but I want to. Okay, so whole code is on this. Can it be seen? The XIO one on the bottom of the screen. Because I'm not sure my keyring works, so. Okay, so is this derivation of our derivative quite understandable? Okay, so this time it's more digestive, yes? Okay.
To mi musisz generalize the
Uh,
rendering.
So with this, we are already able to train this network. Just one thing that we will need is some kind of better activation function. So the most popular one are this is sigmoid one, which is quite easy. So you wanted 0.3 or just because it's 1 plus xpop minus input. Yeah, 0.3 it's beautiful, I think, because it's 1 over or recip 1 plus or successor exponential and negate. So which one you prefer, you may choose. Yeah, the sigmoid is quite okay function, because if we give it, for example, so let's take this to then at the beginning we have some very small numbers, very, very small, and then like at the middle it just jumps to half and then jumps to 1 and it's 1, so it's like so it's basically this one. So it has this nice property that when someone is inspired by biology, it looks like the neural activation somehow. So one last thing that we need is loss function. So to satisfy the AD library, we'll write it as not a function of two variables, but a function of list of our expected input, output, and just output. Yes, thanks. Okay, so I think I okay, now it's fine. This function is like this. We have negation of sum. This is our expected times logarithm of output. And it's sum with something like this. Maybe this will be better, and logarithm. So log just. So many mathematics. Okay, so quality of this function is that if we take loss of something of the same numbers, okay, it's not a number. And why is that? It's because logarithm is not defined for negative numbers. So with sigmoid, we have numbers from 0 to 1, but for 1 this logarithm is for 0, so to don't have problems with numerical errors, we just add some epsilon, so which will be some very small number, and this applies to both logarithms. Another typo, okay, great. It's too much in the morning for me. So now we don't have not a number, but some very, very small number. The same for 2 zeros, because for 2 zeros is symmetric. And if we have difference, then it's quite big as when compared to this. And because we want our derivative of loss function with respect to output, not with respect to expected, so if we take, okay, this is so-called log loss, logarithmic loss function. So maybe it would be better if we call it like this. And if you want gradient of this function, then it's just so this is grade function given by the ID library that will compute our log loss, but let's remind him that this is a polymorphic function. So we need to tell him also that this is polymorphic. Okay, now it type checks, so it's great. So we have this function which gives us a list of 2 functions, if I remember correctly. Yes. No, so it gives us a function that returns 2 values, so this will be gradients with respect to first argument and with respect to a second argument. So we will take our how it was, okay, so everywhere it was first expected then output. We apply it for the list. And then just brutally take the second one. Also, I think we can just use it like this. This will be working. Okay, zero-based indexing. So let's see. Okay, I forgot that I defined it so it would be working like this. So the value seems to be right, because if you have 1 and 1 here, if we have this gradient and we subtract it, then everything will go more to the right. So the bigger values, but this is our biggest value, so this will not change anything. And this is our lowest value, so if you have this positive number here, then we'll go more to the negative side, because we are subtracting. And as this is our minimum, then it will not change anything. So this is exactly what we want from the loss gradient, that if you have proper answer, that it will not change anything. Okay, so some people have came after I promoted, so okay, I love you, Xmonad. Okay, so if someone does not have our sets on my GitHub, there is this file which consists of 10,000 of lines of Haskell parsable pairs. So it's downloading this may take some time, but it's prepared so that it can be parsed with read. So I think this might come in handy. So if could someone post it on Discord? Okay, if this will load.
Oh, it's 49.
So it looks like this. So for each line we have a tuple. So I think it's so where's my Xmonad? Where's my Emacs? Which is more important? Okay.
You're better off cloning the Git repo because Git does some compression and this file compresses very, very well.
I'm sorry?
Don't just download the file, clone the Git repo, it will download a lot faster.
Yes.
Because the file is very compressible and Git does compression on it. The Git clone is done in seconds and the download takes a long time.
So that's quite useful info. So when we have this, I have this in location so to parse it, it's just this is how I called it, by the way. I don't remember. Train set, okay. Okay. So let's abuse our extensions. So let's see if this works. I'm not sure if I reloaded it, so. Okay, so maybe head. If I want to take second one. It's 5, so it's just like it should be. So now we need to make vectors from this. So if you want this to be vector, then we just need to take this from list, so it's quite trivial. So maybe let's get it like this. Second map, because it will be more readable. Well, I talk readable and then I write lambda, so take this with a grain of salt. Okay, so we will use so-called one-hot encoding for the labels, because for labels we have these integers which tell us which number is on the image. So, okay, maybe we should do some pretty printing of these, so you can see that these are indeed images of numbers. They are images 28 on 28. So we have 28 lines of 28 numbers, and each number is the how black is the pixel on this position. But it's all flattened into one long 684 long vector. But this maybe in a moment. So one-hot encoding is something that basic encoding in classification. So we have our index of our class that we want to check if it's the predicted class. So we will create a vector that on the if this is n, then on the nth coordinate will have 1 and every else will be 0. So this will be like saying for one number there's 0 probability that this is this number, and for n there's 100% probability that this is the number that we need. Which we can do just like this. And this will be IO of list of pairs of vector 784 and vector 10, because we have 10 digits that are possible. So let's see if this works. Okay, seems to be working. Oh, and we don't need this bracket. I haven't thought of this. Okay. So the training now is trivial, so let's say that we want some test our training. So let's this in IO. Let's just take 100 examples for now, so it will be fast. Okay, maybe not A, but something more verbose. So. I will do it just with fold. So we have.
What is random network?
I'm sorry.
Where is random network defined?
Okay, it was one of the. Okay, random layer. It should be. Thanks. Okay, so I forgot that I was looking for this function, so let's. And we need our loss function, which was the grad log loss. Our network and the train set. Okay, so we would like to be able to test it. So why not do some eval? Which will just print if it's correct. So to be more verbose. How I called it? It was, I think, something like this. So let's just take 10 of these pairs to see if everything's okay, and we'll just okay, so I forgot we have here another argument, which is the activation function. And this is something I also forgot. So the num constraint in the constructor of network is a little too much. We need to use floating because we want to have logarithms and exponentials. So this is why we created the floating instance at the beginning. And the same goes here. Okay, it looks like it somehow works. If we find the biggest one, which here is on this position, which is fifth one, and we see this is also fifth one. So it somehow approximates. It's still not sure sometimes. Okay, but here is quite sure, so we have it's not so bad for 100 examples, I think. So everyone is there, so or I just got there so fast that.
Can you show the last line?
I'm sorry? down. Maybe I will just hide this and but as I was reminded, we need a little break, and I think I agree with this statement. So let's assume
Right now there is only one layer of neurons.
for now. This is the thing that we will do in the next hour. Okay, so everyone's ready now? Maybe start?
Yeah.
Okay, so what we would like to do now is to have more layers, because we want to have more parameters, because we have too many spare time. We want to have it to take longer time to train. So why not? Let's get to it. So we will extend our definition of network. So we will get to the composition. Which is quite straightforward. It's standard composition. I think we don't need to specify anything here. We just say that it's so we want, okay, we will do it like in a function. So this will be our input and output. This will be input of this, and let's say k. And we will get, okay, not matrix but layer, network. So okay, I made some typo here for sure, so I will just do it like this. Okay, how have I done it? I don't know. That's what happens when you want to be smart.
So you are adding it to the front of the network.
I'm sorry?
You are adding it before the network, like not after, right? Are you adding it to the left of the network or the right?
So this is the first network, and this is the second. So we do it like the normal function composition in this order. It doesn't matter, but I think it will be more better for us. So what we need to do now, we had this function, so now we need to specify how it will behave in the in case that it is a composition. So we have and this is quite straightforward because it's just okay, so maybe this will be network 1 because this is the first one that will get the signal. Okay, so it seems I was wrong, and we need the constraints here, that these are known nuts. Okay, so now the type checker does not bother me, so I think it will be okay. and
Can you show
yes, of course. So maybe I will just. Okay, I always forget which one is it. Okay, so for training examples, this is quite more complicated because the loss gradient function, which we take as a function, as an input, is only needed at the end of the network. So at the beginning, we don't really need this. We only need the gradient with respect to the output of given layer. So why don't we, because thanks to the chain rule, we only take this derivative, which we computed with respect to our output, and just multiplied it. So why don't we take this as an argument? So this will be quite better for us. Which is just a vector of the same dimension as our output. And now we don't need this. But still we need to somehow define what we'll do in case of our composition, and this is quite simpler than it seems. So this whole backpropagation will be just composition of network 2 and network 1. Have our input. Oh, and in this case, because we don't have this function, we don't need expected output, because we don't use it anywhere. We only needed it so we could apply this gradient of our loss function. So let's make it even more simpler. So the same adjustment of type. Okay, so we will only need to train the first one. So what do we need? We need to train this network, we need input to this network. So input, okay, this is the second one, so we'll start with this one. Input to this network is output from this network. So let's get, okay, so I'll keep to the where convention, and
Input to network 2 is from network 1.
and it's from network 1 to network 2.
Okay.
So the network 1, which is the right one, is the first one that's taking the input. It produces output, which is then input to the network 2.
Okay.
So let's do it in this way. How I called it? So we'll just do it recursively. It should work without problem. So okay, so the gradient here is gradient with respect to the output of the composition, and output of the composition is the second network. So to train the second network, we can use just this gradient. But as an input, we'll specify input 2 when input 2, where input 2 is just the output of network 1, so it's just okay, I done some terrible thing. I'm not watching what I'm doing, but okay. And it bothers me again. And it does it because... Okay, that's interesting.
Is it train net 1, train net 2, or the other way around?
Oh, that's right. It should be like this. And now it just tells me that it's not defined. Okay, so that's great. Okay, so we will need to somehow get the gradient for the output of the first network. So here we have our chain rule, but with respect to weights. But the both chains of derivatives diverge at the matrix vector multiplication. So at this point, we can also, because we can reuse this, and I mean this one, to compute the derivative with respect to output of this network. And if we return it with our network, so let's just say that we return also a vector of length of our input. So this will be the gradient that will be passing recursively. So we only need a gradient with respect to the input, which is, if I remember correctly, just matrix vector multiplication of this and our chain, rest of our chain. So there's one problem with this, which is that we have this +1, which we don't need because output of our previous because when we take input, we always consync 1 at the beginning of the vector. So when we backpropagating our gradient, we want to remove the position which belongs to this A, because we don't this 1, because we don't need it. And I think we haven't defined something like this for our vectors. So to not lose our sight from this, but get back to this. We just need some tail. Okay, so to get rid of the typo, Okay, so what is... Okay, so how did I call it? Transpose mat, okay. Now the only adjustment is to add this gradient with respect to input to our output. Bless you. So here we also will need input gradient. So now this will leave not only our train network, but also the gradient with respect to input of our second network, which is gradient with respect to output of our first network. So let's call it and now we are able to train the first one. And the gradient with respect to the input of the first network is just gradient with respect to the input of the whole composition. So this is our okay, so okay, so the compiler does not try to fight with me, so I guess it seems to type check, so maybe it works. Okay.
I have one question. The composition you have defined, right? So it doesn't define with either data or type or new type.
I'm sorry?
Composition.
Yes.
It doesn't define it with either data or type or new type.
Because it's one of the constructors of network.
Okay.
So it's just JDT.
Okay.
Okay. So we may write now version for, let's say, okay, so now we cannot use this as easily, but
Use training example function once again.
I'm sorry?
Could you show that function once again?
Yes, of course. So take your time. Okay, it may be a little too horizontal. So let's say that this is the result. Okay, so in the meantime, maybe I will write a wrapper around this, so that will only extract. So when we train whole network, we don't need the last input gradient because we will not be passing it anywhere. So we can write a wrapper around this, which will make our life easier. And it would be nice to compute this last gradient with respect to output before we start doing here, where we assume we have this vector computed already. So what can we call it? Let's say and here we'll be taking our function, loss function, which is okay. So let's start with the constraints. Okay, so this bracket is not necessary. This is quite straightforward, I think. So we need our derivative, which is just okay, so I forgot about something. No. Okay, because we don't need the output here.
Can you push this on GitHub?
Okay.
I cannot appear to type.
Well, after the when I finish, this will be pushed on GitHub. So you want it now, or
Or could you please do it now because we can't create the new string example function right?
okay? Okay. So, are we ready to get along with this, or? Because the only thing we need to change for now is this, that we change this, and it should be working right now. We'll see. So let's give them first dimension, I don't know, 50. Wow, with type checks, whoa. Okay, so it took him some time, and he will need more examples because we have more parameters. Okay, so this looks a little better. Maybe, maybe not. So let's see if my memory explodes. Maybe we'll just... Okay, so for anyone that is still rewriting, I will get this here. How was it? I don't remember. Okay, so okay, it's not there, but the funny thing here is what we created, because the main thing we created is a memory leak. So okay, it's over the projector, but now I have 37% memory taken, and I.
You can try compiling, it might run faster later.
Yes, it will run faster, but still the memory leak will be there.
No, actually sometimes it works better.
Yes, but I know how to do it, because the only thing we need to change is to give the strict data flag, and the memory leak will go away.
Okay, what does it do?
It just makes the fields of your data constructors strict. Okay, so it seems close or not. it's here it guessed, I guess. Here not exactly. So his best guesses are ones, but it's this is nothing. So let's do it this way. So less examples, but more times. Okay, but not like this. Okay, so it seems to be converging or not. Well, the best way to check this is to overtrain it.
Big false positives.
Yes, it has false positives and quite many of them. So something might be off. Something surely is off because it should be on 5th, not 4th. So
Last one is the most confident.
yes, and it's most confident everywhere, so I'm not sure. So let's see if we can overtrain it on our evaluation set. So this will be the best estimation, and it does not look so good. And I would say it looks very bad. Now it converged. So maybe it's the yes. So I think it may be the learning rate. So it's too so for the things on the screen it seems to be working. So let's see this is okay. This one is okay. This one is also okay. So we could some learning rate adaptation algorithm, but I don't think we have time. But I think it's mostly the learning rate here. So if we maybe lower the learning rate and pass it more examples, it will converge better. But it seems quite okay. Maybe the number of Well, we could see how, but maybe on the compiled one. So everyone wants to see code, or is everyone satisfied with the code and just want to see blank screen for 5 minutes and then see what the results are?
I'm actually curious to see the results myself.
Yeah. So let's create a main. Okay. No. By the way, nice sticker on the laptop.
Oh, thank you. A lot of allies here.
So we have this function, that's all we need. So we'll take all the 10,000 examples? I think yes. And how many times you want to pass them? 2, 3, 10?
5.
Okay, your call. So if someone will want to bother me that we're watching empty screen for 5 minutes, then it's all him. So Xmonad still doesn't like me.
As long as we can run into the break a little bit, I guess it's fine.
So right now we have 2 layers.
Yes, we have 2 layers. Okay, so nice watching blank screen. I hope you will like this view. So I will monitor the memory if the leak is really gone. But
So why would you use multiple layers, like in reality?
they generalize better, because the more parameters you have, the more interesting structure of your this space of outputs is. So if the space of desired outputs is not so simple, it has very curvatures, very steep places, many steep places, then the more parameters you have, the more you can adjust it. So it will pass better for the more exotic examples.
Is there any name for this algorithm that we are implementing?
It's backpropagation algorithm.
What's the algorithm?
Backpropagation.
Backpropagation.
Ooh,
Finished.
quite fast. Oh, it converged, I think. It looks fine.
Looks pretty good.
Yeah. So, congratulations on implementing your backpropagation algorithm.